Instead of doing Taylor and Maclaurin polynomials, now we're going to be doing Taylor and Maclaurin series. Okay, here's our first example. We have f of x equals sine of x. We're centered at 0, so this is, in fact, a Maclaurin series. And we want to find the interval of convergence. Now, the directions say use the definition, which means you want to grind this out and work it out the long way, rather than using the memorized formula. So we're going to go ahead and start taking derivatives. Of course, the derivative of sine of x is cosine of x. The second derivative would be negative sine. The third derivative would be negative cosine, and so forth. Okay, since we're centered at 0, we can go ahead and take the sine of 0, which of course is 0, cosine of 0, which is 1, and so on. And that'll give us the coefficients that we need for our Taylor series. Okay, I'm going to clean this up, and when we write the Taylor series, again, it's a Maclaurin series, we will go ahead and have 0 plus 1, and this time it'll be x to the first over 1 factorial, no x squareds, negative 1 x to the third over 3 factorial, and so on. Okay, now that we have that written out, we have to go ahead and put it into sigma notation. So again, the Taylor series is going to be the sum. And obviously we're going to have an infinity up top here. I will start it with n equals 0. And we can see that the signs are changing here. We have positive 1 and then negative 1. Obviously I'm not going to worry about the 0 terms, so we have to figure out a way to get those out of there. I do notice that in the denominator, we're going to have 1 factorial, 3 factorial, eventually 5 factorial, and so forth. So I'm going to say 2n plus 1 factorial. And that works because if n is 0, you're going to get the 1 factorial right here. If n is 1, you put the 1 in, you're going to get 3 factorial, and so forth and so on. So that's cool. I also know that the power matches that, so it's going to be x to the 2n plus 1. And then finally, we need the alternating component. So I'm going to go negative 1, and it's either going to be to the n or maybe to the n plus 1 or n minus 1. Let's see, if I start with 0 and I plug the 0 in to here, it's going to be negative 1 to the 0, which is positive. I do want it to start positive and then go negative later. So that's actually good, and so that's my formula. So I'll go ahead and circle that. And I'm done with the first part, which is find the Taylor series centered at C. So that's been taken care of. Now I want to go ahead and I want to find the interval of convergence. And of course, like always, we start that out by using the ratio test. Okay, so for the interval of convergence, we have the limit as n approaches infinity. And again, it's absolute value. And it's going to be all the n's raised by a power divided by just the regular Taylor series that we found. So I'm going to go ahead and write that in now. You may notice I have a pair of 2n plus 3's. Remember, when n becomes n plus 1, it's really 2n plus 1 plus 1. So that's going to make the 2n plus 3 with the factorial and the power. All right, now I can cancel, of course. Like always, whenever you do ratio tests, the alternating component, the negative 1's, are going to cancel away, especially with the absolute value. Also, you can cancel the x to the powers. Since 2n plus 3 is always 2 larger than 2n plus 1, the denominator will be gone, it'll be a 1, and the numerator will simply be x squared, because again, there's 2 extra x's up there. Similarly, you have your other parts, being the factorials. 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1, but then it starts to cancel with this factorial. The rest of them are gone. And so you're just left with x squared over quantity 2n plus 3 times quantity 2n plus 2. Since that's heading towards infinity, the denominator is going to be infinity times infinity. Again, keep in mind that n is heading towards infinity, so these will both be infinities, which is going to make this entire deal right here 0. Okay, since it's a ratio test and we want this to converge, we make sure it's less than 1. But since 0 is always less than 1, that means that this is going to converge all the time. So the interval of convergence is simply all real numbers. Or if you prefer, you can use interval notation and say negative infinity to positive infinity. So that's number 1. Okay, here we are with number 2, same set of instructions. It says use the definition to find the Taylor series. So again, I have to generate it. This time it's not Maclaurin, it is centered at pi over 2. So again, I'll start out by taking the original function, cosine of 2x, and I'm going to go ahead and just take derivatives as I go. So first derivative, of course, is negative sine with a chain rule. And I just keep doing the other derivatives. We'll do second power, here's third. And finally, a fourth derivative. And you can see the coefficients are growing because of the chain rules. And now I have to center it at pi over 2. And so I'm going to go ahead and do that now. Okay, so you can see what we have with our coefficients. And I'm going to go ahead and write the Taylor series right now. Keep in mind that we're centered at pi over 2. Okay, I'm going to put those coefficients in. The first was a negative 1. I'm going to skip the 0 term, so then we had a 4. You may remember we had a negative 16th, and so forth. Now remember, these are only even powers, so 0 factorial, 2 factorial, 4 factorial, and so forth. Again, it's centered at c, which is pi over 2, so it's not just x, it's x minus pi over 2 for each of these. This is to the 0 power, which is completely unnecessary, but I'm going to write it anyway so you can see the form. And the other x minus pi over 2's are here as well. And their powers match the factorials, so 2 and 4. And that just keeps going forever. So that's the Taylor series. So that's the first thing that we wanted, was to find the Taylor series. I am going to write it as a sum as well, just like I did in example number 1. So here's your sigma. Again, just like before, we're going to take it from 0 to infinity. 0 is the index. We are changing signs each time, so we are going to have an alternating component be negative 1 to the, this time I want it to be n plus 1. And the reason why is we are starting with a negative, and that way if we plug the 0 in, we're going to have negative 1 to the first, which is this negative 1 right here. So you can also put negative 1 to the n minus 1. That's fine as well, because that's going to work. And then you finish off with the factorials. If I want the denominators to be 0 factorial, 2 factorial, 4 factorial, and so forth, I need a 2n down here, factorial. That way I skip over all the odd powers. And then the same thing up top, I would have the x minus pi over 2 also going to the same 2n power. That way I skip all the odd terms and odd powers. I left a space because I'm going to put 4 to the n right here. The first term had 4 to the first. I'm sorry, pardon me, 4 to the 0, which is 1. That's why you don't see anything here. This is 4 to the first. 16 is 4 squared. Again, the negative has already been taken care of because I've got the negative 1 to the n plus 1 in front there. So that is the official formula for the Taylor series. So that part's done. Now again, just like the other example, I have to find the interval of convergence. And as always, we use the ratio test. Okay, as we're well aware, we have to take the limit as n approaches infinity. We will crank all the n's up by a power, and we'll divide by the reciprocal of what we have. All right, let me write it out. All right, well, because of the absolute values, the negative 1's will always just reduce to 1 over 1. One of them will be positive, one will be negative. I don't even know which, but the absolute value takes care of that. Also, we have one additional 4 up in the numerator. So when we cancel away n of them, there'll be 1 left up here. That's a 4. The x minus pi over 2's, there are 2 extras up in the numerator as well. So we have a pair of those. That's going to cancel those away. So for the factorials now, we have, let's see, 2n plus 2 times 2n plus 1 times 2n and so forth. But the rest of it's just going to cancel with this up here. That's going to cancel that part out. So all in all, we're left with this, the 4, and a pair of x minus pi over 2's. And down here in the denominator, we're left with those 2 parentheses. But those 2 parentheses are where it's at because they both have n's, and both of those n's are heading towards infinity, making the denominator ginormous, and the numerator not all that big. And so as n heads towards infinity, this entire group of fractions is heading closer and closer and closer to a limit of 0. And since 0 is less than 1, like all the time, the interval of convergence is all real numbers. If you don't like the fancy old English looking R abbreviation, you can always say interval notation. You can say from negative infinity to positive infinity. That covers the whole world. Notice once again I do not hard bracket infinities because we technically can't reach them. But we have reached the end of this section, which is great. So that's the end of day 1. We'll catch you for day 2 next. See you then.